Morning, folks. Somebody told me that, or Desiree was saying that they had seen the space station overhead, so it looks like the space station is going to be overhead tonight. And then I guess this is the end. If you have a good clear horizon, you can see it at about 20 or 30 degrees, but we don't have any good clear horizon. Because, 10 degrees is really just sort of just above the horizon. 10 degrees is your fist. So really your only hope of seeing it is tonight.
Well, actually, Dion, we watched it Friday and Saturday, and it said 10 degrees, but it was high. It was like straight above us. Well, I live in Montport, so we had to look towards Thibodeau. But like I said, Saturday night, it went over the moon. The moon was full. So the degrees thing is kind of off, I think.
Oh, okay. Well, you can try it these other nights. You can try it Wednesday. Tonight's supposed to be cloudy.
Yeah, but if you watch the exact time that it said it was supposed to pass, just watch whatever's moving fast.
Okay. And it's really bright too, right?
It's bright and it moves fast.
Logan?
I got this app on my phone. It's called Sky Guide, and it gives me updates whenever anything's about to happen or something. I got a lot of updates for the Iridium satellites. Whenever they pass, like by the horizon towards the sun, it flares.
Oh, cool.
So I mean, and
What's it called? Spot the Sky?
it's a Sky Guide.
Sky Guide. Okay. It's a free app. Oh, okay. Yeah. Sky Guide. But this is just on spotthestation.net, something like that, if you want to see it. All right. And then somebody also asked about the exam. The exam is coming up. It's a week from Friday. Is that before a break? Do we have a break after that?
I hope so. I think our break is like the end of March.
Oh, okay.
Easter break, yeah.
Oh, okay. So anyway, 1 week from Friday, we'll have the exam, and it will likely cover Chapter 3. I know that seems like a lot, and it is, because I compressed the first exam to have not as much material, but then these next 3 exams will have more material. There's just more time in between the exams. So once we get through Chapter 2, which is pretty long, like we'll probably be in Chapter 2 for much of this week, if not all of it. Chapter 3 is really short. It's really just on current. There's a couple of easy definitions, and it would be good to have it on the exam so you'll have a nice, easy question from that chapter. I said, I don't like to say things are easy, but it is fairly straightforward. It's just the definition of current, really, and Ohm's law. We won't get into circuits. And those of you in lab, I know not all of you are in lab, but those of you who are in lab have already seen that. All right. Let's pick up with capacitors. We're going to shift gears now and get into electrical circuits. So we'll see capacitors, and then we'll do capacitor circuits, both series, parallel, and combination circuits. And then we'll get into resistors, the definition of resistors and what resistors are, Ohm's law, which you may have already seen before. And then we'll do resistors in series, parallel, and combination circuits, and then finally we'll get into multi-loop circuits, where we apply some certain rules to resistor circuits. And then we'll see RC circuits, where we'll combine the resistors and the capacitors. And then I think from there, it's like we'll do magnetic fields, but then we're in circuits for the rest of the year. We'll see inductors, LRC circuits, LC circuits. Inductors is the L. So you'll have inductor, resistor, capacitor circuits, inductor, capacitor circuits, and inductor, resistor circuits. And so we'll spend quite a bit of time in that, dealing with AC electricity. So a lot of circuits for the rest of the semester. But first, capacitors. We're going to deal with a parallel plate capacitor. That means that you have two plates that are parallel to one another. They don't touch, so there's never actually any current that flows across the capacitor. When I talk about current, we'll see that in Chapter 3, that it means the flow of charge. So if I have charges flowing inside a wire or through a wire, that's current. You've probably heard of current before. But with capacitors, you don't have any current, at least after they're completely charged. We'll talk about that later. But if I have two parallel plates, they store charges on them. And that's really the purpose of a capacitor, is to store charge or to store energy. So a capacitor consists of two metal plates of area A. So they have a certain area, and then they're separated by a distance d. So this is the distance d. And we'll see how capacitors are actually made, but in theory, they're just two metal plates. They have a certain area, and they're separated by a distance d. And we'll see that in practice, they're a little bit different from that. When connected to a battery, the capacitor becomes charged and stores energy that can be used later. So if I connect it to a battery, I can think of, again, we know that protons aren't actually moving, but I can think of protons traveling along this wire. And so this side gets positively charged. It gets a certain charge plus Q. And then this side gets negatively charged in an equal but opposite way. So I get equal number of positive and negative charges on each plate. We'll see when we get into capacitors in series, and this is actually an induced charge. So one plate gets charged, and then the other plate gets an induced charge. Remember, an induced charge is when I don't have touching things. So one of them gets charged, and then the other gets an induced charge. The capacitance of a capacitor is defined by the amount of charge it holds. With a certain potential difference, or with a certain voltage between the plates. I'll start calling this voltages at this time as we're talking about circuits. But to call it a potential difference is also correct, but often we'll sort of use those terms interchangeably. Potential difference, remember, describes the difference in potential between 2 points. Similarly, I'll use voltage to mean the same thing. So when I'm talking about a battery, for example, here we're talking about a battery, the potential difference is the difference in potential here and here, the difference in those two. And in this case, it's a 12-volt potential difference. So our capacitance is going to be defined by the charge that it holds divided by the potential difference. The units of capacitor are the farad. This is after Michael Faraday. And so it's abbreviated as 1 farad. We use a capital F for farad. And a farad is equal to a coulomb per volt. That's just based on this definition. And so you could break it down further into its basic SI units. Let's see, what would that be? That would be 1 coulomb per basic SI units. Joules per coulomb is our volts. So that's going to be 1 coulomb squared over joule, which you could break it down further. 1 coulomb squared, what's a joule? It's a kilogram meter squared per second squared. And so the basic SI units are going to be 1 coulomb squared, second squared, kilogram meter squared. Certainly don't memorize that. Just remember the basic SI units are coulombs per volt, which is based on this definition of capacitance. But then remember that we can further break it down into those three, or here actually are 4 basic measurements. Mass, length, time, and charge is now one of our basic SI units. So for the figure that we had on the previous page, if we want to know the capacitance, if the charge here was 24, if the charge was 24 microcoulombs, then we would define the capacitance. C would be Q over V, which is going to be 24 over 12, which would be 2 microfarads. Often we'll see this expression not as C is equal to Q over V, but we'll see it instead as Q equals CV. And in fact, that's how I'll write it from now on. Q is equal to CV. the charge on a capacitor is equal to its capacitance times its voltage. A good way to think about capacitance is to think about capacitance as the capacity to store charge. What is the device's capacity to store charge? And that'll give you an idea of what the capacitance is. It really just describes how much charge can this device hold on its plates. And that capacity to store charge is based on its geometrical qualities. So here, let's try this quick test. Capacitor C1, we'll see one similar to this later. Capacitor C1 is connected across a battery of 5 volts. An identical capacitor is connected across a battery of 2 volts. Which capacitor has the most charge? Which capacitor is storing the most charge? All right, I'll stop at 45. 45. Okay, let's see. We're sort of split between A and B. Remember, our charge here is equal to C times V. If I have two identical capacitors, that means that this remains constant. So the capacitor with the bigger voltage will have the bigger charge. Now let's see. Capacitor C1 was connected across 5 volts. Capacitor C2 was connected across 2 volts. So which one will have the bigger charge? C1 will have the bigger charge. So A is going to be our right answer here. Don't worry, you'll get the hang of it. Once you get sort of the hang of these relationships, they become a lot easier. Because, you know, really with capacitors, the relationships aren't that complicated. It's just sort of internalizing them and getting used to them. So if you didn't get it now, don't sweat it. We'll have lots more questions for you to practice with. All right, let's try this. We're going to look at the parallel plate capacitor. Remember, it's 2 plates. They are separated by a distance d, and they have a certain area A. And so I want you to think about how that area and how that separation distance will affect the amount of charge that the capacitor can store. And then we'll, from that, develop an expression for the capacitance. So first of all, how is the amount of charge stored affected if the area is increased? So if I make the area of my plates bigger, what do you think that will affect the amount of charge that you can store? Will the amount of charge increase, the amount of charge you can store decrease, or will it still store the same amount of charge? If I make the plates bigger, how does that affect the amount of charge that I can store? You don't have any reason to know this answer right off, but I think you can figure it out.
When you say a plate, like 2 pieces of metal?
2 pieces of metal, right? A square plate, 2 pieces of metal plate, 2 square metal plates. If I make them bigger, how does that affect the amount of charge that they can store? They're still the same distance apart, but I just make them bigger. How does that affect the amount of charge they can store? More or less, or is it the same? Oh, okay, let's see. I'll stop at 110. 110. Okay, good. A is the right answer. If I make those plates bigger, it can store more charge. Let's see. Did I tell you all the 0-8 joke I did, right? Yeah. Did I tell you the pony joke? The pony walks into a bar joke? I don't remember. I might have told you last time. The pony walks into a bar. The pony walks into a bar. And he says, "Hey, bartender, can I have a drink?" And the bartender says, "What?" And the pony says, "Can I have a drink?" And the bartender says, "What?" And then the pony says, "Oh, I'm sorry. I'm just a little horse." Told you that one before?
No.
No, okay, good. All right. All right, so how is the amount of stored charge affected if the separation between the plates is increased? So now the area remains constant, but I pull those plates apart. What happens to the total amount of charge? All right, let's stop at 25, or we'll go to 28. 28. Okay, good. B is the right answer. If I pull those plates apart, it can store less charge. And again, that's not really something that you would necessarily know, but I think it is a little bit intuitive. If I make the plates bigger, there's just more area for the charges to go onto. If I pull the plates apart, then that potential that is actually causing the charges to go onto them, it's like it weakens a bit when I pull those plates apart. So we have a couple different relationships. With this one, we have that C is proportional to A, and with this one, we have that C is proportional to 1 over D. And so we can develop an expression. We're first going to have a proportionality constant, epsilon naught. We've seen this before, if you recall. It's related to our K value. Our K value was equal to 1 over 4 pi epsilon naught. So it's wrapped up in Coulomb's law, related to the force between two charges. So it's epsilon naught times A over D. So this is our capacitance. We have now two expressions for capacitance. We have that one, and then we also have this one. Q is equal to CV. So I can define my capacitance in two ways. I can define it based on the geometry of my capacitor, what is the area and the distance between them, and then I can also define it based on the voltage and the charge stored. In practice, this is the way that you would measure the capacitance, but it should also theoretically go to this, that if I have certain plates that are separated by a certain distance, then I can figure out their capacitance. Okay, let's try this one. Remember these two expressions, Q is equal to CV, and C is equal to epsilon naught A over D. And here I have a capacitor that's hooked up to a battery with a voltage of 12 volts. After you charge the capacitor, the battery is removed. What is the voltage across the capacitor if the area of the plates is doubled? That thing about the battery being removed is pretty important because it means that you charge up the capacitor, it gets a certain amount of charge, and then you remove the battery, and that means that the amount of charge is going to remain constant. The capacitor is not going to lose charge, but it's also not going to gain any extra charge. Okay, so that sentence means that the charge will remain constant because you take the battery away. It can't get any extra charge. And then you change the area of the plates. What then will happen to the voltage of the capacitor? Makes a nice way to create a variable voltage supply. Not real common to do it that way, but you can do it this way. Are sort of all over the board. Let me give you a little hint here. So I'm keeping my charge constant. This is not changing. I'm increasing my area of the plates by a factor of 2. So you want to ask yourself, what is that going to do to the capacitance of the capacitor? And then ask yourself, well, if I change the capacitor by that amount, what happens to the voltage? So that's the thought process you should be going through. First of all, how does the capacitor change when I change its area? And then, how does this capacitor change? And then, well, if that capacitor changes by that amount, how should my voltage change across this capacitor? All right, let's do about 8 more seconds. I'll stop at 2:15. 2:15. Just guess if you're not sure. Okay, so we started out with 12 volts. Now, what's going to happen to my capacitance when I increase the area? It's going to double. It's going to increase by a factor of 2 because everything else remains constant. So I double my capacitance. If my charge is remaining constant, then my voltage will have to drop by a factor of half. So initially my voltage was 12 volts, so now it's going to be 6 volts. So C is right here. I guess if you put B, you probably thought that, well, maybe you thought that your capacitance was decreasing by a half, or probably more likely is like you just sort of saw this 2 here, the capacitance increased by 2, and you thought, well, voltage has to increase by 2 as well. It's probably what you were thinking, but remember, if my charge remains constant, whatever I do on the right-hand side also has to remain constant. I can't get a multiplicative factor. I can't get a 2 on the right-hand side. I only have to have a 1, and the 2 and the 1/2 will, cancel one another out. Don't worry, we'll see some more questions like that when we do the concept test. Another thing about capacitors is they often have dielectrics in between them. A dielectric is just an insulator. It's an insulating material. Usually it's going to be wax-covered paper. If you ever take apart a capacitor, I'll show you a video where this guy takes apart a capacitor. They're just 2 metal plates, and then they have this wax-covered paper in between them. This dielectric, it serves a couple purposes. One of the purposes is to increase the capacitance of the capacitor. I'm just going to call them caps now. To increase the capacitance of the cap or capacitor, it increases the capacity to store charge. And it increases it by a certain amount. When I have a capacitor, let's say it's equal to, I don't know, 10 microfarads, and then I put in a dielectric that has a dielectric constant of, say, 1.5, then my capacitance then will be 15 microfarads. So now we have this new expression for the capacitance that our more general expression is that C is equal to kappa epsilon naught A over D. If I don't have a dielectric constant, then kappa is just equal to 1. Now, you always have a dielectric of some sort, even if it's air. I guess you could have it in a vacuum, but air has a dielectric constant that's just slightly above 1. But some of these other dielectric constants can be up to a factor of 2 or even higher. They can increase the capacitance of your capacitor. The real purpose, though, for a dielectric is, what do you think? That's more practical. I mean, that's sort of what happens when you stick a dielectric in between 2 metal plates. But what do you think is the real practical purpose for a dielectric? What is it about those 2 plates in a capacitor that has to always be true? And what now? Okay, they do have opposite charge. Yeah, you're right about that. But just practically, what is it called? What kind of capacitor? What about the distance between the 2? Needs to stay the same. That means that they're parallel, right? It's a parallel plate capacitor. So that distance doesn't change. That means the plates, they can't touch. Because if the plates touch, they're just 2 metal plates. If they touch, it's just going to be like a piece of wire. Okay? So your capacitor, the plates of your capacitor can never ever touch. And that's really the practical purpose of the dielectric, is to keep the 2 plates of the capacitor separate. To keep them from touching. Because again, if they touch, it's just like it's a piece of wire. It doesn't function anymore. I have a video. I'll show you a picture on the next page, and I'll show you a little video. Go down from here. So usually what you get is you have 2 metal plates. So those are our 2 metal plates, and they'll be connected to some leads. So these are just wires. And then in between the 2 metal plates, you have your dielectric. And y'all remember roly-poly? Did y'all ever go to roly-poly? You did go to roly-poly? That used to be at Tuskie's, and then it was an ice cream shop, and now it's like a cell phone store or whatever. It's sort of like a roly-poly. You put a tortilla with a piece of meat, and then actually you would put another tortilla, and then you would fold the whole thing up. Now they would only do one tortilla, but you can imagine two tortillas. It would be sort of like that, because then you take these metal plates with the dielectric, and you roll it up like a roly-poly, except they have the dielectric in between them. You don't have to draw this if you don't want. And then, you have your other tortilla here. Anyway, the dielectric is there just sort of to keep them from touching, keep those two metal plates from touching. And so this is a picture of a capacitor that's been blown up. You can see it's all rolled up like one of those roly-poly wraps. Let me show you this video. He actually cuts apart a capacitor and shows you the parts. And then he also builds a capacitor, which if you know any grade school kids, this is a great project for a science fair or something, to build a capacitor and explore ways to increase the amount of charge that it can hold. It's a great science fair project. Let me pull it up right quick. Yeah, I think I have it here. So if you want to go back and watch the rest of it, it's on YouTube. You can just search, make Zine capacitor. But anyway, that's sort of the basics of a capacitor and how it stores charge. Let's try this little quick test. So you could see a problem on the next test where you just have to calculate what is the capacitance of a given capacitor. So let's just practice that. Here I give you the dimensions. Don't forget the dielectric constant, and just tell me what is the capacitance of that capacitor. I'll remind you what is epsilon naught. It's 8.85 times 10 to the minus 12. And this is going to be, what is it, farads per meter, I think? It had different units before, but now we can call it farads. That's right. Yeah, farads per meter for the basic units. Yeah, Brandon?
Is the area per capacitor, or?
No, you just consider the area of one of the plates. That's a good question. So you don't double the area ever. You just consider the area of one plate. Doing pretty well on this. I'll wrap it up here in about, say 10 seconds, 15 maybe. I'll stop at 235, 235. All right, good. B is the right answer. This is really just sort of knowing the formula and putting in the right numbers. So C is kappa epsilon naught A over D. Kappa here is 1.5. That's my dielectric constant. Epsilon naught is 8.85 times 10 to the minus 12. And then I have my area, which is 0.4. It's already an SI unit, so I just keep it there. And then the distance is 1 micron, or 1 times 10 to the minus 6 meters. So that gives me my Capacitance 5.3 times 10 to the minus 6. Isn't that right? Yeah. 10 to the minus 6 farads. Or 5.3 microfarads. Okay? Could see that it would probably be part of a bigger problem where I give you a capacitor in a circuit, and then but I also give you the dimensions of that capacitor, and you have to figure out the capacitance of it. Let's do a few clicker questions. Just have a few on this bit. These are in the back of your book if you want to follow along. Oh, did we do this one? 2.7a? Is this the last one we left off at? Yeah, okay, let's do this one right quick. This is sort of going back to what we had done before. Which requires, I have a positive charge at point P, which requires the most work to move that positive charge to which point? To point 1, 2, 3, or 4. Think about our definition of work, right? Work is force times displacement, or F dot D, and then ask yourself what is the direction of the force, and then which motion will require the most work to move it from point P to point 1, point 2, point 3, or point 4. Alrighty. I'll stop at, say, 1 minute. Share your answer. Some of you probably saw the answer up on the screen. Did you? Or you're just really sharp? Y'all are really sharp. Okay, I'll stop at 1:05. Okay, good. A is the right answer. Remember, if I have a positive charge in an electric field, the force is in the same direction as the electric field. That's the force due to the electric field. So if I'm moving a charge, I have to apply a force in this direction to go towards position 1. So this is going to give me positive work. On the other hand, if I'm moving in this direction, I have to hold it back, right? Like that dog on a leash, I have to hold it back and then let it move. So this is actually doing negative work to move it in this direction. This one requires 0 work, and this one is somewhere in between. So position 1 requires the most work. Okay, I just told you this. Which one's 0 work? 3 is 0 work, because my force and my displacement are perpendicular. So we'll skip that one. Okay, so a connector C1, our capacitor C1 is connected across a battery of 5 volts. C2 is across a battery of 10 volts. Which one has the most charge? C1, C2, the same, or does it depend on something else that's not stated? Alrighty, I'll stop at, say, 37. Just a few more seconds, just guess if you don't know. Alright, awesome. We had the same question basically earlier. Since the capacitance is the same, Q is equal to CV. Capacitance is the same. The one with the bigger voltage has the bigger charge. So the one with the bigger voltage is C2. So B is the right answer. What happens when a frog's car breaks down? What happens when a frog's car breaks down? It gets towed away. What must be done to a capacitor in order to increase the amount of charge that it can hold? Can you increase the area of the plates, decrease the separation between the plates, decrease the area of the plates? A or B, B or C, which of those? All right, a few more seconds. I'll stop at 38. 38. Okay, let's see, D, that is right. So D is right. Remember, C is kappa epsilon naught A over D. That's on your equation sheet, by the way. If I increase the area of the plates, or if I decrease the distance, both of those will increase the capacitance. So it's both A and B will increase the amount of charge it can hold. Okay, this is similar to the one we had before, but it's a little bit different. I have it hooked up to a battery of voltage 400 volts. It stays connected to the battery. So when I say that, that means that the voltage will remain constant. What happens to the voltage or the charge if I double the plate spacing? So I increase D by a factor of 2. What happens to the voltage or the charge? Okay, doing pretty well. I'll stop in about 10 seconds at 110. Just guess if you don't know. I'm stopping. Okay, great. C is right. The charge will decrease. So C is kappa epsilon naught A over D. I am increasing what? The plate spacing. So this goes up. That means the capacity to store charge, the capacitance, decreases. And since Q is equal to CV, this remains constant. This is going down. So this goes down. In fact, this goes down by a factor of a half because I increase this by a factor of 2. I decrease that by a factor of a half. So I decrease this by a factor of a half. So I also get a factor of a half there. So the charge will decrease by a factor of a half, by 2. Here we have a very similar question, although now I'm disconnecting it from the charging battery, and I'm doubling the plate spacing. Right. Yeah, potential difference in voltage, you can use those interchangeably. So we'll sort of do that now. I'll move toward using voltage. That means that the total amount of charge doesn't change. Remember before when we had that question when we disconnected it from the battery? We said because it's no longer connected to the battery, the total amount of charge remains the same as it was initially. So Q is remaining constant.
So that's like it's disconnected.
Right, it is disconnected. Right. So Q remains constant. All right. This may seem a little, I don't know, esoteric because it's very difficult to change the geometry of your capacitor, but it is not difficult to change the overall capacitance. And we'll see that when we get into circuits, that I can take a circuit and just add in or take out a capacitor, and that will change the overall capacitance, which is really what we're doing, allowing you to change either the voltage or the stored charge. All right, so I'll stop at 145. Okay, so here, my C is epsilon naught A over D. I have that kappa in there. I am doubling the plate spacing. That means I'm decreasing C by a half. Q is equal to CV. This remains constant. This is going down by a factor of a half. So this goes up by a factor of 2. It initially was 400 volts. Now it's going to be 800 volts. So D is the right answer. Very good. You'll certainly see some of these type questions on the exam in the multiple choice part, where you just have to think about changing the capacitor, what does that do to the voltage and or the charge. We'll come back to this. Let me give you the symbols for the circuits that we'll be using. In fact, when we get after the chapter on magnetism, we'll see some different symbols as we start to add inductors and stuff like that into our circuits. But for now, we're just going to deal with batteries and capacitors, and soon we'll see resistors as well. If you ever look at circuit diagrams, you've probably seen these before, and they might have some slight variation, but they'll look a lot like what we have. So batteries are a long line, two parallel lines, one that's long, one that's smaller. Sometimes, I'll just use this symbol, but sometimes you might see a plus and a minus to represent the positive and negative sides. On a battery too, this is usually our red side, this is usually our black side. The black is sometimes called the ground side. We'll talk about what that means in chapter 4. You'll often see a number below it, and we'll use that just to represent what is the voltage. Sometimes in circuits, you'll see multiple lines like that. The number of lines is proportional to the actual voltage of the battery, so that's why they use multiple lines. But we'll use this symbol for batteries or voltage supplies, power supplies. For capacitors, the symbol that we'll use will look like this. It looks like a capacitor, although sometimes in circuits, because this can sometimes look a lot like the battery, depending upon how you draw your lines, sometimes people will use this symbol, a straight line and a sort of semicircle. We'll use this symbol. We usually put the capacitance, say 2 microfarads or whatever, below the resistor or below the capacitor. And then for resistors, it's almost universally the symbol used for a resistor. You'll have the value for it, say 2 ohms. We'll see the unit for resistance in chapter 3. You can see some variations with this. We won't use them, but for example, in case you ever see them, you might have a resistor that looks like this, that has an arrow through it. This is a variable resistor. A resistor that can change its resistance. Like, for example, the dial on your light switch, the dimmer switch, that's a variable resistor. You can also see one that might look like this. You usually have a resistor with a little arrow and a line coming off, and it goes off into the circuit. This is also a variable resistor, but we'll only use this symbol for our circuits. All right. We're going to see combinations of capacitors. Hold on, let me look at my... Actually, I think we'll just stop there, y'all. All right, and we'll pick up with this on, what is the day? Sorry, I'm not quite off here. Monday. I'll see y'all at Thursday. Capacitors are a big chapter, okay? Don't let them fall to the wayside.